Somewhere in the Milky Way tonight, a planet roughly the mass of Jupiter is drifting through absolute darkness, following no orbit at all, warmed by nothing but the heat still leaking out of its own interior. Astronomers now suspect there could be more of these starless planets adrift in our galaxy than there are stars to count. This is the story of how a world loses its sun, or is born without ever having one, and what becomes of it afterward, the violent gravitational encounters that fling young planets into the void between the stars, the newborn giants that condense alone out of collapsing clouds of gas, and never had a star to begin with, and the strange, patient methods that let us find something completely dark set against a background of nothing. Along the way, we will ask the biggest question this fact raises. If a planet can keep its own inner fire burning long after any star that once lit it is gone, could something, somewhere, still be alive down there in the permanent night? A planet is usually defined by its orbit. It circles a star held on a long curved path by gravity, lit and warmed by that star's output, and counted as a member of that star's family of worlds. For most of the history of astronomy, this definition seemed complete enough that nobody thought to question it. Then, in the early years of this century, a handful of survey telescopes watching the crowded centre of the Milky Way began turning up something that did not fit the definition at all. The surveys responsible, run out of Poland and New Zealand under names like OGLE and MOE, were built to look for something else entirely, the way a foreground object's gravity can act like a lens, briefly brightening the light of a star behind it as the two happen to align from Earth's point of view. Astronomers call this gravitational microlensing. Most of the events these surveys caught involved an ordinary star doing the lensing, but in 2011, a team led by the astronomer Takahiro Sumi published an analysis of 2 years of observations that included a separate, smaller population of lensing events, short, isolated brightening flickers, with no star visible either before or after, consistent with objects roughly the mass of Jupiter and nothing else nearby. The implication was strange enough that it took real caution to state plainly. These were planet-sized objects alone, with no star anywhere near them. Based on the rate at which the surveys caught these isolated events against the much larger number of star lensing events, the team estimated that free-floating planets of roughly Jupiter's mass could outnumber main sequence stars in the galaxy by something like a factor of 2. Later reanalyses have narrowed and debated the exact number, and the true population size remains an open question in astronomy. But the core finding held up under scrutiny. Planets with no star to orbit are not a rare curiosity. They may be one of the most common kinds of planet the galaxy makes. It helps to be precise about what the word means here, because science fiction has used looser versions of it for decades. A free-floating planet, sometimes called a rogue planet or an isolated planetary mass object, is a body in the general mass range of a planet that is not gravitationally bound to any star. It is not moving toward one, not slingshotting past one, not on some enormous multi-million-year orbit that will eventually bring it back. It has no star at all, now or for the foreseeable future of its own existence. Whatever light it carries, it generates itself. That single fact reframes everything that follows in this story. 2 very different processes can produce a world like this. One is violent. A planet that formed normally, in orbit around a star, and was later thrown out of that system entirely by a close encounter with a larger sibling. The other is quiet. An object that formed the way a star forms, out of a collapsing cloud of gas and dust, but fell short of the mass needed to ignite nuclear fusion in its core, and so never became a star or belonged to one in the first place. Both processes are known to happen. Distinguishing which one produced any particular starless planet, once it is found, is one of the genuinely hard problems in the field, because a planet ejected from a system and a planet that formed alone can end up looking almost identical from a distance. What both kinds of objects share is a kind of astronomical invisibility that makes them exceptionally difficult to study. A planet orbiting a star is found, in the overwhelming majority of cases, because of what it does to that star's light. The faint dimming as it passes in front, the tiny wobble it induces by tugging on the star gravitationally. A planet with no star produces none of these signatures, because there is no starlight to interrupt, and no stellar wobble to measure. It is, from Earth, simply a very faint, very cold, very dark point that does not announce itself in any of the usual ways. Finding one at all means catching it doing almost nothing, for a few days or weeks against an almost uniformly dark sky. The 2011 discovery mattered because it was the first solid statistical evidence that this invisible population was not just theoretically possible but numerous. It did not name individual planets or map their orbits, because free-floating planets do not have orbits worth mapping. It established something more basic, and in its way more startling, that the galaxy's planetary census, built almost entirely on planets we can see because of their stars, was very likely missing a huge and largely uncounted class of worlds that keep no company at all. Understanding how that class of worlds comes to exist starts not with the moment a planet is thrown into darkness, but earlier in the crowded, chaotic disk of gas and dust where every planet, starbound or not, begins its life. Before a planet can be thrown out of a system, it first has to be built inside one. That process begins roughly the same way every time, whether the star it produces will end up hosting 8 planets, 100, or eventually none. A star is born from a cloud of gas and dust, mostly hydrogen, that collapses under its own gravity. As the cloud falls inward, it spins faster, the same way a skater spins faster by pulling in their arms, and the spin flattens most of the infalling material into a wide, rotating disk around the newborn star called a protoplanetary disk. This disk can stretch for tens of billions of kilometers, far wider than the orbit of Neptune around our own sun, and it holds the raw material for every planet, moon, asteroid, and comet the system will ever have. Inside that disk, dust grains no larger than particles of smoke begin colliding and sticking together, first through simple static forces and later through their own weak gravity, building up over hundreds of thousands of years from specks to pebbles to boulders to objects the size of a small moon. Once a body reaches a certain size, usually a few hundred kilometers across, its gravity becomes strong enough to pull in everything nearby along its orbital path, and growth accelerates rapidly. These larger bodies are called planetary embryos, and a single disk can produce dozens of them in its first few million years. What happens next depends heavily on distance from the star. Close in, where it is warm enough that ice cannot survive, embryos can only be built from rock and metal, which limits how large they can grow. This is almost certainly why the 4 innermost planets of our own solar system, Mercury, Venus, Earth and Mars, are all comparatively small, rocky worlds. Farther out, beyond a boundary sometimes called the frost line, ices such as frozen water and frozen carbon dioxide remain solid, adding enormously to the raw material available. Embryos in this colder region can grow rock and ice cores many times the mass of Earth, and once such a core is large enough, it can begin pulling in the disk's abundant hydrogen and helium gas directly, ballooning within a few million years into a gas giant. This is the accepted explanation for why Jupiter and Saturn, both far larger than any inner planet, sit well beyond the frost line in our own system, and observations of hundreds of other young star systems show the same general pattern. This is also where the story starts to turn dangerous for the planets involved. A system's gas giants, forming fast and growing enormous, do not stay quietly in place while the rest of the disk finishes its work around them. Their gravity is now strong enough to disturb everything nearby, nudging smaller embryos onto new paths, scattering leftover debris, and in some cases drifting inward or outward themselves as they interact with the remaining gas in the disk, a process called migration. Current models of our own solar system's early history, built from computer simulations that reproduce the present-day arrangement of planets and asteroids with reasonable accuracy, suggest that Jupiter itself may have migrated inward toward roughly where Mars now orbits, then reversed and migrated back outward again, in a sequence researchers have nicknamed the Grand Tack. If a planet as large as Jupiter can move that dramatically within our own system's youth, the same disruption in other, more crowded systems can be considerably more severe. By the time a young star system is a few tens of millions of years old, most of the gas in its disk has either been pulled into the star and its planets, or blown away by the star's own radiation, and the wild early growth phase ends. What remains is a smaller number of full-sized planets, considerably fewer than the number of embryos that started out, because many embryos in a crowded young disk do not survive to become planets at all. Some are absorbed into larger bodies through collisions, some are thrown into their star and destroyed, and some, as the next chapter follows in detail, are thrown clear out of the system entirely, launched into the empty space between the stars by exactly the kind of gravitational disturbance that gas giants are uniquely capable of causing. The disk that builds a planet, in other words, is also the arena in which that planet's fate as either a star-bound world or a starless wanderer gets decided, often within the first few tens of millions of years of a system's existence, long before anything resembling the mature, settled solar system we know today has taken shape. A newly formed planetary system does not settle into the calm, clockwork arrangement we associate with the solar system today. In its first 100 million years or so, it is closer to a slow-motion demolition derby, with a handful of massive bodies working out, through repeated gravitational near-misses, which of them gets to keep a stable orbit and which does not. The basic mechanism is called planet-planet scattering, and it works on the same principle as a slingshot. When two planets pass close to each other, their mutual gravity exchanges energy between them. In almost every close encounter, one planet gains orbital energy at the other's expense. The winner is pushed onto a wider, often more elongated orbit, while the loser is pushed onto a tighter one, or in the more extreme cases, is accelerated so much that it exceeds the system's escape velocity entirely and leaves for good. Escape velocity is simply the speed an object needs to break free of a gravitational pull permanently, rather than falling back or settling into a new orbit. For a planet near a sun-sized star, that speed is measured in tens of kilometers per second, and a strong enough gravitational kick from a giant neighbor can supply it in a single pass. Giant planets are especially good at this, because their gravity is strong enough to significantly perturb a neighboring world's orbit from a considerable distance, while smaller rocky planets generally lack the mass to do the same to each other. This is why the objects most often implicated in ejection events, in both simulations and in the handful of real systems where we can reconstruct some of the history, tend to be gas giants or the smaller planets caught near them, rather than small rocky worlds acting on each other directly. A second, related mechanism involves what astronomers call orbital resonance, a situation where two planets' orbital periods form a simple ratio, such as one planet completing exactly 2 orbits for every 1 orbit of another. Resonances can be stabilizing, locking planets into a predictable long-term rhythm, but they can also be destabilizing if a system passes through a resonance during a period of active migration, repeatedly reinforcing small gravitational tugs until an orbit becomes wildly elongated. Several observed systems around other stars appear to show orbital architectures consistent with having passed through a violent resonant instability early in their history, based on the mathematical signatures left behind in their present-day spacing. To make the distances and speeds involved feel less abstract, imagine our own Earth, at its average distance of about 150 million kilometers from the Sun, receiving a gravitational kick strong enough to double its orbital speed within the span of a single afternoon. A kick on that scale, delivered by a close pass with something the mass of Jupiter or larger, is roughly the order of disturbance these simulations are describing, though the specific planet involved in any real system is very rarely Earth-sized, since giant planets are the ones doing most of both the kicking and the getting kicked. The entire process, from a system's first violent instability to its final settled arrangement, is thought to typically play out within the first tens of millions of years after the star itself forms, a period that is a small fraction of even a young star's total lifetime, but during which the majority of a system's eventual planet ejections take place. How often does an ejection actually happen? Simulations of young multi-giant planet systems run thousands of times over with slightly different starting conditions to sample the range of possible outcomes, find that a meaningful fraction of them, plausibly on the order of one system in 10 to 1 in 3, depending on the initial number and spacing of giant planets, end up losing at least one planet to full ejection before the system settles down. Applied across the roughly 200 billion or more star systems astronomers estimate exist in the Milky Way, even a conservative version of that fraction implies an enormous number of ejection events over the galaxy's history, each one launching a planet permanently out of its birth system. The planet on the losing end of one of these encounters experiences something almost impossible to picture from the inside, a sudden, decisive acceleration delivered in the space of hours by a close pass with a much larger neighbor that converts a stable orbit into a one-way trajectory out of the system entirely. What that moment of departure actually looks like and what becomes of the ejected world afterward is where the story goes next. Orbits come in 2 basic families, distinguished by a single number: how much total energy the orbiting body has. A body with negative total orbital energy, meaning its kinetic energy of motion is smaller than the gravitational energy binding it to its star, follows a closed path, an ellipse, and returns to the same points again and again, indefinitely. A body with positive total orbital energy is not bound at all. Its path is an open curve, a hyperbola, and once it has that much energy it is not going to return, ever, regardless of how the star's gravity continues to pull on it from a distance. A planet involved in a violent gravitational encounter with a giant neighbour can cross from the first category into the second within a single close pass, sometimes lasting only hours as measured from the planet's own point of view. The star's gravity does not simply switch off once this happens. It continues to decelerate the departing planet for a long time afterward, exactly the way Earth's gravity continues to slow a thrown ball, even after it has left your hand. But for an unbound object, that deceleration can never fully cancel the outward motion. The planet keeps slowing asymptotically, without ever stopping or turning back. The practical result is that the planet spends a long time still noticeably influenced by its former star's gravity even as it becomes, for all functional purposes, gone. It typically crosses the orbital distance of the system's outermost planet, within a few decades of the ejection event, moving far faster at this stage than any bound planet ever would at that distance, and continues to slow gradually as it moves through what is sometimes called the outer scattered region, a sparse zone of icy debris analogous to our own solar system's Kuiper belt. Only after it has travelled well beyond that debris, typically over a period of thousands of years, does its speed relative to its former star settle into something close to constant, at which point it is moving through true interstellar space, no longer meaningfully bound to, or influenced by, anything it left behind. What does an observer on such a planet, purely as a thought experiment, actually witness during this departure? In the hours immediately around the encounter itself, the giant planet responsible for the ejection would loom enormous and then recede with startling speed, an effect of the close pass's short duration. Over the following years, the planet's former star would visibly dim, not because the star itself changes, but because the planet's own increasing distance from it obeys the same inverse square relationship that makes any light source fainter the farther away you view it from. A star that once dominated the sky as a brilliant disk would, within a few centuries, be reduced to an unremarkable point of light, and within a few thousand years to something too faint to distinguish easily from the general background of other equally distant stars. This fading is the physical event underlying the first of this episode's recurring images. A single point of light in a young world's sky, dimming steadily not because anything catastrophic destroys it, but because the simple mechanical fact of ever-increasing distance eventually erases it from view. There is nothing dramatic about the final stage of this fade. It happens slowly enough that no single moment marks the planet as officially starless. It simply, gradually, is. What the planet keeps, through all of this, is whatever heat it had already built up during its formation, energy stored from the gravitational compression that assembled it in the first place. And in the case of a gas giant, additional heat still slowly radiating outward from its interior as it continues to very gradually contract under its own weight, a process that can continue at a low level for billions of years. This internal heat, not any star, becomes the ejected planet's only ongoing energy source for the remainder of its existence, and it is the reason a newly ejected giant planet is not, in fact, uniformly frozen and inert the moment its star disappears from view. Whether that inherited warmth is enough to support anything more interesting than a slowly cooling ball of gas or rock is a question this episode returns to later, once the different kinds of starless planet and the different amounts of internal heat each is likely to carry have both been laid out properly. Once a planet has fully escaped its birth system, it enters an environment almost nothing in the solar system prepares us to imagine clearly. Interstellar space, the vast close to empty volume that separates one star system from the next. In the part of the Milky Way's disk where our own Sun sits, the average distance between neighbouring stars is roughly 5 light-years, which is to say, roughly 47 trillion kilometres, a useful anchor for a number that size. Light itself, the fastest thing there is, takes about 5 years to cross that distance, while the fastest spacecraft humans have ever launched would take on the order of tens of thousands of years to cover the same span. A planet drifting at a typical ejection speed, somewhere in the range of a few kilometres per second relative to its former system, would take an even longer, comparably staggering stretch of time, plausibly tens of thousands to hundreds of thousands of years, to drift anywhere close to another star, and there is no guarantee its path takes it near one at all. Most of an ejected planet's existence, statistically, is simply spent in the open gap between systems, not en route to anywhere in particular. That gap is not a featureless void in every respect. It contains an extremely thin distribution of gas, mostly hydrogen, at densities so low that a cubic centimetre of it typically holds only a handful of atoms, compared to the roughly 25 sextillion molecules in the same volume of air at Earth's surface. It also carries a steady flux of cosmic rays, high-energy particles accelerated by exploding stars and other violent events elsewhere in the galaxy, along with the collective, extremely dilute starlight of every star in the Milky Way combined. None of this delivers anything close to the warmth or the intensity of light a planet receives from its own nearby star. The background temperature of interstellar space itself, set almost entirely by the residual glow left over from the universe's early history, sits at a bone-chilling 2.7 Kelvin, only a few degrees above absolute zero, the coldest temperature physically possible. An ejected planet, then, moves from an environment shaped by one dominant nearby energy source, its former star, into one with essentially no external energy source at all worth mentioning. Whatever heat the planet radiates from this point onward comes from inside it, and nowhere else. For a gas giant with a large reservoir of formation heat still slowly leaking outward, this internal glow can remain measurably warmer than the surrounding voids too. 7 Kelvin background for a very long time, though it steadily fades as the planet radiates that stored heat away, and has nothing external to replace it. For a smaller rocky ejected planet, with far less mass, and therefore far less stored heat to begin with, the cooling proceeds faster and the eventual equilibrium temperature settles far closer to the ambient cold of space itself. This raises an obvious and important asymmetry that matters for everything discussed later in this episode. Not every starless planet is starless in the same way, and not every starless planet is equally cold. A large gas giant, ejected relatively recently in astronomical terms, carries enough leftover heat to remain, by the standards of interstellar space, comparatively warm for a genuinely long time, plausibly hundreds of millions of years. A small rocky world, by contrast, cools far more quickly, and an old one, ejected billions of years ago, is likely to have settled close to the ambient temperature of the space around it long ago. The population of starless planets drifting through the galaxy right now, in other words, spans a considerable range from recently ejected giants still glowing faintly with their own internal warmth, to ancient, thoroughly frozen bodies that have had all the time in the universe's history to lose whatever heat they ever had. The planets discussed so far all share one origin story: a star, a system, a violent departure. But this is not the only path that leads to a planet with no star. An entirely separate population of starless worlds, as the next chapter turns to, never had a system to be ejected from in the first place, because they formed alone from the very beginning, condensing directly out of the same interstellar material that also gives rise to stars, only never quite managing to become one. Not every planet with no star to orbit got that way by being thrown out of a system. A separate and, by some estimates, comparably large population appears to have formed with no star involved at any point in its history, arising instead through a smaller scale version of the same basic process that builds stars themselves. Stars form when a sufficiently dense clump within a giant molecular cloud, an enormous cold accumulation of gas and dust that can span dozens of light years, collapses under its own gravity. Astronomers studying these clouds with modern telescopes have found that the collapsing clumps do not come in only one size. The same basic gravitational instability that produces a full-sized star can, in smaller pockets of turbulence within the same cloud, produce a collapsing clump with a total mass in the same rough range as a large planet, a few times the mass of Jupiter, rather than the hundreds of times Jupiter's mass typical of even a small star. Whether such an object should be called a planet at all is a genuinely live question among astronomers, and the honest answer is that the terminology has not fully settled. A body formed this way, condensing directly from a collapsing cloud rather than growing up gradually inside a disk around an existing star, is sometimes called a sub-brown dwarf, sometimes a free floating planetary mass object, and sometimes simply a rogue planet, depending on which researcher is doing the naming and which formation detail they consider most important. What nearly everyone agrees on is the physical boundary that separates this category from a true star. Fusion, the nuclear process that powers ordinary stars by fusing hydrogen nuclei together and releasing energy, requires a core temperature and pressure that only builds up in objects above roughly 80 times the mass of Jupiter. Below that threshold, but above roughly 13 times Jupiter's mass, an object can still fuse a rarer form of hydrogen, called deuterium for a brief period, generating a small amount of energy for perhaps 100 million years before that fuel runs out. Objects in this middle range are called brown dwarfs, sometimes informally described as failed stars. Below 13 Jupiter masses, there is no fusion of any kind ever, and the object simply carries whatever heat it was born with, slowly cooling for the rest of its existence, exactly like an ejected gas giant. This is the category astronomers place the isolated, cloud-collapsed rogue planets into. Massive enough to have formed the way a star forms, but never massive enough to ignite even briefly. Direct observational evidence for this population comes from infrared surveys of very young star-forming regions, areas of active star birth, typically only a few million years old, where astronomers have identified a number of isolated, planet-mass objects with no companion star anywhere nearby and no evidence of ever having had one, based on their location well outside any known system, and the absence of any disrupted orbital debris that an ejection would typically leave behind. Several of the youngest such objects found in these surveys are still warm enough, from the leftover heat of their own recent formation, to be photographed directly in infrared light, something that is essentially never possible for an older, cooler rogue planet regardless of how it formed. Why does the distinction between the two formation pathways, ejected versus born alone, matter for the rest of this story? It matters because it changes what we should expect to find when we go looking. An ejected planet, having previously formed inside a disk around a star, is likely to be broadly similar in composition and structure to the planets we already know from our own solar system. It may have a rocky or icy core, it may carry an atmosphere accumulated during its time in the disk, and depending on how long ago the ejection happened, it may or may not still have significant leftover heat. An isolated, cloud-collapsed object, by contrast, formed the way a star's very outer layers form, from collapsing gas directly, and is expected to be predominantly hydrogen and helium in composition, more uniformly gas giant-like, without necessarily having gone through the slower, rockier assembly process that builds a typical planet inside a disk. Both kinds of object end up, from the outside, looking broadly similar, dark, cold or lukewarm, alone, and extremely difficult to find. The next chapter turns to exactly how astronomers manage to find either kind at all, given that neither one comes with a star to give away its location. Finding an object that emits essentially no light of its own, is not orbiting anything that would give away its position, and is scattered across a galaxy tens of thousands of light years across, requires giving up on looking for the object directly and instead looking for what it briefly does to the light of something else. Gravitational microlensing as a consequence of general relativity, Albert Einstein's theory describing gravity as a curvature of space itself rather than a simple attractive force. Any mass bends the path of light passing near it, including a mass far too dim to see. When a foreground object, a star, a planet, anything with mass, happens to pass almost exactly between Earth and a much more distant background star, its gravity acts like an imperfect lens, focusing a small amount of the background star's light toward Earth, and making that star appear briefly, measurably brighter than usual, before fading back to normal once the alignment passes. Crucially, this brightening happens whether or not the foreground object emits any light of its own. A completely dark, starless planet lenses light exactly as effectively, for its mass, as a star would. The practical challenge is that this kind of alignment, precise enough to produce a detectable brightening, is extraordinarily rare for any single background star, and the survey telescopes hunting for the effect therefore monitor hundreds of millions of stars simultaneously, night after night, concentrated on the densely packed stellar field toward the center of the Milky Way, where the sheer number of background stars makes chance alignments happen often enough to be statistically useful. The resulting brightness measurement over time, called a light curve, has a distinctive shape, a smooth rise to a peak brightness and a smooth symmetrical decline back to normal, with the total duration of the event directly related to the mass of the lensing object. A star-sized lens typically produces an event lasting weeks to months. A planet-sized lens produces an event lasting hours to a few days, simply because a less massive object's gravitational influence sweeps past the alignment point faster. This duration dependence is exactly what let the 2011 survey, and subsequent surveys since, distinguish planet mass lensing events from star mass ones, and further distinguish free-floating planet events, which show no accompanying longer-term signature from a host star from ordinary bound exoplanet events, where a shorter planet signature appears as a brief secondary blip, superimposed on a longer stellar lensing event. An isolated, unaccompanied short event, with no such secondary structure and no evidence of a host star zone's separate lensing signal, is the specific signature that indicates a free-floating planet rather than a star-bound one. Microlensing has one significant limitation that shapes everything else about how the search for starless planets has to proceed. The alignment that produces a detectable event is a one-time occurrence. Once the foreground object has moved out of alignment, the event is over, permanently. There is no second chance to observe the same object doing the same thing again. And in the overwhelming majority of cases, there is no way to follow up and directly confirm what the lensing object actually was, since it has, by definition, moved on into the surrounding darkness and given no further signal of any kind. This means microlensing is excellent at establishing statistically, from the aggregate rate of many events, how common starless planets probably are across the galaxy as a whole, but it is fundamentally unable to identify, name, or study any specific individual object it detects, beyond a rough estimate of its mass at the moment of the event. For that kind of individual, detailed study, astronomers need a different technique entirely, one that does not depend on a chance alignment and can, in principle, be repeated and refined over time. That technique exists, but it only works for a narrow and specific subset of starless planets, the youngest and warmest ones still glowing with enough of their own leftover formation heat to be caught directly, rather than inferred indirectly from what they do to somebody else's light. A handful of the youngest starless planets found so far were not caught through microlensing's brief, unrepeatable flicker. They were photographed directly, sitting quietly in infrared images of very young star-forming regions, glowing faintly on their own. This is possible because of a simple fact about how planets, and in fact stars too, initially acquire their heat. Gravitational collapse itself generates enormous amounts of energy, as material falling inward converts its gravitational potential energy into heat through compression, in essentially the same way that compressing air in a bicycle pump makes the pump barrel warm to the touch, only on a scale involving the equivalent of Jupiter-sized masses of material collapsing over a period of thousands to millions of years. By the time a newly formed gas giant-sized object, whether it formed inside a disk around a star or collapsed alone from a molecular cloud, has finished assembling itself, its interior can be extraordinarily hot, and its surface can radiate at a temperature well over 1,000 degrees Celsius, purely from this leftover formation heat, with no external energy source contributing anything at all. A temperature that high, for an object with no other light source nearby, produces measurable infrared radiation, the same general category of light, just at longer wavelengths than visible light, that a very hot stove or a heated metal bar gives off. Infrared telescopes, including ground-based observatories fitted with adaptive optics that correct for the blurring effect of Earth's atmosphere, and space-based infrared telescopes operating above the atmosphere entirely, can in principle detect this glow directly, distinguishing a warm, isolated planet mass object from the cold, empty background of space around it. The catch is time. This formation heat does not last. A gas giant-sized object radiates away its leftover heat steadily over time, cooling according to well-understood physical relationships between mass, surface area, and radiated power that astronomers can model with reasonable confidence. Within roughly the first 100 million years of its existence, an isolated planet mass object's temperature drops dramatically, and by the time it is a few 100 million years old, its surface has typically cooled to temperatures too low to be detected with current infrared telescopes at any meaningful distance, even though the object itself has not gone anywhere and has not changed in any fundamental way, other than simply cooling down. This means direct imaging, unlike microlensing, is not a general-purpose search method for finding starless planets of any age. It is a narrow window that only works for objects that are, in astronomical terms, extremely young, typically less than about 20 million years old, meaning they must be found still sitting relatively close to the young star-forming region that produced them, since a starless planet's own gradual drift is unlikely to have carried it far from its birthplace in such a comparatively short span of time. Every starless planet astronomers have managed to image directly so far fits this profile. Found in or near a known, young star-forming region, warm enough from recent formation to stand out clearly against the cold infrared background, and too young to have drifted far or cooled significantly. What this leaves us with, taken together with microlensing, is a genuinely lopsided picture of the starless planet population. Microlensing tells us, in aggregate, that these objects are likely to be common across the galaxy as a whole, of every age, but almost never lets us examine an individual one closely. Direct imaging lets us examine specific individual objects in real detail, including in some cases estimating their atmospheric composition from the pattern of infrared light they emit, but only for the small, young, still warm minority. The vast majority of the population this episode has been describing, older, cooler, scattered thoroughly through interstellar space, far from any young star-forming region, remains essentially unobservable with current technology, known to exist mainly through statistical inference, rather than direct confirmation. What we can say with more confidence, drawing on both methods together, is roughly what these objects are actually like physically, which is where this episode turns next. A planet with no star is not automatically a dead, uniformly frozen ball. What keeps a rocky or icy world from settling completely to the ambient near absolute zero temperature of interstellar space is, perhaps surprisingly, largely the same mechanism that keeps our own planet's interior warm today, roughly 4.6 billion years after Earth itself formed. Earth is not warm inside because of anything the sun does. The sun's warmth reaches only the surface and does not meaningfully heat the interior at all. Earth's interior is warm, hot enough to keep a large portion of its mantle in a slow semi-molten, flowing state and its outer core in a liquid state, because of two separate internal sources. The first is leftover heat from Earth's own violent formation, when the collisions and gravitational compression that assembled the planet in the first place generated enormous amounts of heat that has still not fully escaped, even after billions of years, because rock is a poor conductor and heat escapes from a planet-sized body only very slowly. The second, and today the larger of the two contributions, is radiogenic heat, the continuous, slow radioactive decay of naturally occurring unstable elements, chiefly uranium, thorium, and a radioactive form of potassium, that were incorporated into the planet when it formed and have been steadily releasing small amounts of energy as they decay ever since. Together, these two sources currently deliver an estimated 47 trillion watts of heat outward through Earth's surface, an enormous number in absolute terms. Though spread across the planet's entire surface area, it amounts to only a gentle background warmth, far too weak to feel directly and utterly swamped at the surface by the far larger amount of energy Earth receives from the sun. A starless, rocky or icy planet has exactly the same two internal heat sources available to it, having formed by broadly the same processes as Earth, but it is missing the overwhelming external contribution from a star that on a star-bound planet like Earth normally dominates the surface energy budget entirely. Strip the sun's contribution away, and what remains for such a world is only this internal radiogenic and residual formation warmth, working outward from the interior with nothing external to compete against or wash it out. What this internal heat can plausibly do to a planet's surface and interior depends heavily on the planet's size and composition, and it is here that current models genuinely diverge, with real unresolved uncertainty. For a very large rocky world, several times Earth's mass, models generally suggest enough internal heat could persist to keep a mantle geologically active for billions of years, potentially driving ongoing volcanic activity or plate tectonics at the surface, even in the total absence of any external warmth, similar in mechanism, though considerably reduced in overall intensity, to how Jupiter's moon Io is kept volcanically active today by tidal heating rather than radiogenic heat, a related but distinct internal heat source discussed later in this episode. For a smaller world closer to Earth's own mass, the internal heat budget is comparably smaller, and current estimates are more divided on whether it would be sufficient to sustain meaningful geological activity over billions of years, or whether such a world would gradually settle into a largely inert, frozen state despite its internal heat, simply because that heat, while non-zero, may not be large enough relative to the planet's size to keep pace with how quickly heat escapes into the cold of surrounding space. For a gas giant-sized starless planet, the situation is somewhat different again, because gas giants retain a much larger fraction of their original formation heat for a much longer time, owing to their sheer size and the excellent insulating properties of a thick hydrogen and helium atmosphere. Even Jupiter itself, comfortably warmed by the sun though it also is, radiates measurably more total energy outward than it receives from the sun, a fact confirmed by direct measurement, and the excess is attributed to Jupiter's own slow ongoing gravitational contraction, still releasing formation-era heat 4.6 billion years after the planet assembled. A starless gas giant of similar size, receiving no external warmth at all, would still carry this same internal heat engine, and depending on its age since formation or ejection, could plausibly maintain a surprisingly active interior, with cloud bands, storms, and internal convection driven entirely by heat with no external source whatsoever. What all of this adds up to is a genuinely counterintuitive picture. A planet with no sun is not, by that fact alone, a planet with no internal activity, no warmth, and no possibility of anything happening beneath its surface. It is simply a planet running entirely on the energy it was born with, or generates internally, rather than the energy it receives from outside. Whether that internal budget is ever large enough to matter for something as significant as an atmosphere, or as significant as the conditions life might require, is where the story turns next. An atmosphere on any planet is held onto the surface by gravity and kept from escaping into space partly by its own weight, and in the case of a starbound planet, partly by the ongoing warmth that keeps its gas molecules moving quickly enough to behave as a gas rather than settling out as a liquid or a solid. Remove the star, and that second factor changes completely. For a rocky Earth mass or smaller starless planet, the physics here is fairly stark, and current models are reasonably confident about the general outcome, even if the exact numbers involved remain uncertain. Without external warmth, and relying only on whatever modest internal heat the planet's interior still generates, most common atmospheric gases would gradually cool toward the surface temperature the planet is settling toward, which for an older, thoroughly cooled rocky world sitting in interstellar space would be extremely cold, plausibly within a few tens of degrees of interstellar space's own 2.7 Kelvin background. At those temperatures, gases that make up Earth's own atmosphere today, nitrogen, oxygen, carbon dioxide, would not remain gases at all. Nitrogen freezes solid at roughly minus 210 degrees Celsius, and models of atmospheric loss on a cooling, starless, rocky planet generally suggest that within a relatively short span of time, plausibly on the order of a few million years for a smaller world, the bulk of any atmosphere the planet once had would condense out directly onto the surface as a layer of frost or ice, rather than escaping into space or remaining gaseous. This produces a picture that is genuinely different from the common assumption that an atmosphere would simply blow away or evaporate into the vacuum of space once a planet leaves its star. It would not evaporate. If anything, it would do close to the opposite. It would settle, fall and freeze in place, blanketing the surface in a solid layer of what used to be its air. A visitor to such a world, again purely as a thought experiment grounded in this physics, would not find an airless, exposed rocky surface of the kind we see on Earth's own airless moon. They would more likely find a surface coated in a frozen crust of what was once atmosphere, its texture and thickness, depending on exactly what gases the original atmosphere contained, and how the planet's specific internal heat budget interacts with that frozen layer over time. A sufficiently massive rocky planet, however, several times Earth's mass, changes this calculation meaningfully for two separate reasons that current research treats as genuinely significant. First, its own internal heat budget, scaling up with its larger size, could be enough to keep at least a portion of a thick enough atmosphere from fully freezing, particularly closer to a warmer interior, or in regions where geological activity, if the planet retains any, adds localized heat. Second, and more importantly for the specific case of hydrogen, a heavier planet's stronger gravity is considerably better at retaining light gases like hydrogen and helium against loss into space in the first place, even at extremely low temperatures, where those particular gases, unlike nitrogen or oxygen, would remain gaseous almost regardless of temperature, since hydrogen and helium have such low freezing points that they stay gaseous or liquid down to temperatures far colder even than interstellar space's ambient chill. Gas giants, unsurprisingly, follow an entirely different set of rules because their atmospheres are their bulk, not a thin surface layer that can meaningfully separate from the planet and freeze away. A starless gas giant retains essentially its entire atmosphere regardless of external temperature, because that atmosphere, composed overwhelmingly of hydrogen and helium held under crushing internal pressure, is not going anywhere. It is not a separable layer sitting loosely on a solid surface the way a rocky planet's air is, but a genuinely enormous fraction of the planet's total mass, bound by gravity from the inside as much as from the outside. What changes for a starless gas giant is not whether it keeps an atmosphere, but how that atmosphere behaves without external sunlight driving weather patterns, the way sunlight drives weather on a star-bound gas giant like Jupiter or Saturn. Models generally suggest weather on such a world would instead be driven almost entirely by the planet's own internal heat, rising from the interior and circulating outward, producing cloud bands and storm systems with a different overall structure and pace than anything sunlight-driven weather produces, though the details remain an area of active, ongoing modelling rather than settled fact. The picture that emerges across both rocky and gaseous starless planets is not the uniform, featureless deep freeze the phrase starless planet might initially suggest. It is instead a genuinely varied set of possible surfaces and atmospheres, shaped heavily by size, composition, and the specific balance between internal heat and external cold, with some of the most interesting possibilities, discussed shortly, arising specifically on the larger, more massive end of this range. By this point in the story, a natural question has been building. Just how many of these starless worlds are actually out there? The honest answer is that astronomers do not know precisely, and are unlikely to know precisely for a long time, but the range of estimates that has emerged from more than a decade microlensing surveys is itself worth taking seriously. A useful reference point first, the Milky Way is estimated to contain somewhere between 100 billion and 400 billion stars, a number so large that it resists intuitive comparison, though one way to feel its scale is this: if every star in the galaxy were a single grain of sand, the total would fill a volume considerably larger than a moving truck, and yet each individual grain in that pile would represent an entire star system, potentially with its own planets, its own history, its own now vanished or never-present starless worlds cast off from it. The 2011 Sumi survey, discussed in this episode's opening chapter, produced an estimate that free-floating Jupiter-mass planets could be roughly twice as numerous as main sequence stars, based on the rate of short-duration, unaccompanied microlensing events detected over roughly 2 years of observation. That headline number drew considerable attention, but it has also been revisited and debated since. A 2017 reanalysis by a different research team, examining an expanded and refined dataset, found a lower, though still substantial, rate of these short events, suggesting the true population might be smaller than the original estimate, though still likely comparable in order of magnitude to the galaxy's stellar population rather than dramatically smaller. More recent survey work using additional telescopes and longer observation baselines has continued to refine the number without resolving the underlying uncertainty entirely. The current honest state of the science is that free-floating, Jupiter-sized planets appear to be at least common, plausibly on a similar order of magnitude to stars themselves, but the specific multiplying factor, whether it is closer to 1, 2, or several times the stellar population, remains genuinely unsettled. A further complication, and an important one, is that all of these estimates are specifically calibrated to Jupiter mass and larger objects, because those are the objects current microlensing surveys are most sensitive to detecting reliably. Smaller starless planets, in the rough mass range of Earth or Neptune, almost certainly also exist in significant numbers, produced by exactly the same ejection and isolated collapse mechanisms discussed earlier in this episode, but current survey technology has much greater difficulty detecting the correspondingly shorter, fainter microlensing events these smaller masses would produce. If smaller starless planets turn out to be even a modest multiple more common than Jupiter-sized ones, following the general pattern seen among star-bound exoplanets, where smaller planets are found to be considerably more numerous than large ones, once detection biases are accounted for, then the true total population of starless planets of all sizes could be substantially larger again than even the higher-end estimates currently discussed. What can be said with real confidence, setting aside the specific multiplying factor, is the general shape of the conclusion. Free-floating planets are not a rare astronomical curiosity, a strange edge case turned up by one unusual survey. They appear to be, at minimum, a population comparable in scale to the galaxy's population of stars, and quite possibly considerably larger once smaller undetected objects are accounted for. Multiplied across the roughly 100 billion galaxies current estimates suggest exist in the observable universe, a number arrived at through deep imaging surveys that count galaxies down to very faint brightness limits. This same basic physical process, giant planets destabilizing young systems, and clouds collapsing directly into planet mass objects, has very likely been playing out in essentially every one of those galaxies for as long as stars and planets have existed anywhere. The scale of this estimate has a real consequence for how astronomers think about planets in general, one that the next chapter turns to directly. If starless planets are genuinely this common, the question of whether they can hold on to something as significant as a moon, or as significant as the conditions for life, stops being a curiosity about a handful of unusual objects and becomes a meaningful question about what might be the single most common outcome for a planet anywhere in the galaxy. A planet violently ejected from its system does not necessarily leave everything behind. If that planet had moons, a real and important question follows immediately. Does the moon go with it, or is the moon left behind, orbiting a star that its planet has just abandoned? The answer, worked out through gravitational simulations of ejection events, depends almost entirely on how tightly the moon was bound to its planet, compared to how strongly it was influenced by the star. A moon in a close, tight orbit around its planet, the way our own moon orbits Earth at an average distance of about 384,000 kilometers, or the way Jupiter's 4 large Galilean moons orbit Jupiter at distances ranging from about 420,000 to 1.9 million kilometers, is overwhelmingly dominated gravitationally by its planet, not by the star, even while the whole system still orbits that star normally. When the planet is ejected, this close binding generally means the moon goes along for the ride, its orbit around the planet essentially undisturbed by the sudden violent change happening to the planet's own path around the star, provided the ejection event itself, and any close encounter with a third body that caused it, does not also pass close enough to directly disrupt the moon's own orbit around the planet. A moon in a much wider, more distant orbit around its planet is more vulnerable, because at greater distances a moon's motion starts to be influenced meaningfully by the star's gravity as well as the planet's, and a sudden violent change in the planet's own path can more easily disrupt or sever such a loosely bound moon's orbit, either flinging the moon off on its own separate trajectory, potentially into interstellar space as a starless object in its own right, or leaving it in some kind of altered, unstable orbit around the planet that eventually resolves one way or the other. Simulations of ejection events generally find that most of a planet's closer, more tightly bound moons survive intact, while its more distant, loosely bound moons, if it has any, face meaningfully higher odds of being separated during the event itself. This matters enormously for the question of what an ejected planet's surviving moon system might be capable of, because a moon retained by its planet after ejection is not simply along for a cold, dark ride. It remains subject to a heat source distinct from both the radiogenic decay and residual formation heat discussed earlier in this episode. Tidal heating, the continuous internal warming produced by a moon's gravitational interaction with its planet, as the two flex and stretch each other slightly with every orbit, converting a portion of that gravitational energy directly into heat inside the moon. This is not a hypothetical mechanism, it is the confirmed, measured explanation for why Jupiter's moon Io is the most volcanically active body known anywhere in the solar system, and why Jupiter's moon Europa and Saturn's moon Enceladus are both believed, based on strong indirect evidence including observed water plumes at Enceladus, to maintain liquid water oceans beneath their icy surfaces, entirely independent of any warmth from the sun. A moon orbiting a gas giant that has itself been ejected into starless interstellar space could, in principle, continue experiencing exactly this same tidal heating mechanism, entirely undisturbed by the ejection, because tidal heating depends only on the moon's orbital relationship to its planet, not on anything the star was doing. This means a starless gas giant with a close orbiting moon is a genuine candidate for maintaining a subsurface liquid water ocean, warmed by tidal flexing with no sunlight involved at any point in the process, in exactly the same basic way Europa and Enceladus are believed to maintain their oceans today, while still for the moment orbiting the Sun. Current models suggest such a moon, once ejected along with its planet into the cold of interstellar space, could plausibly sustain this kind of internally warmed ocean indefinitely, or at least for a very long span of time, since the tidal heating mechanism itself has no dependence on external sunlight, and would continue essentially unaffected by the surrounding environment. This is, quietly, one of the more significant implications to come out of the population estimates discussed in the previous chapter. If starless planets are genuinely common, and if a meaningful fraction of them are gas giants that retained at least one close orbiting moon through their ejection, then subsurface, tidally warmed liquid water oceans, sealed away from the cold and the dark by a shell of ice, may not be a rare curiosity confined to a small number of moons in our own solar system. They may exist, current models suggest, on a genuinely significant number of the wandering starless worlds scattered throughout the galaxy, each one entirely on its own, carrying a private ocean that has never once been touched by sunlight. Every question this episode has traced so far, about how a planet ends up with no star, how warm it might stay, whether it keeps its moons, whether those moons could hold onto liquid water, converges on the single biggest question any of it raises. Could something be alive down there? The honest starting point for this question is that nearly all life as we understand it, at every scale, ultimately depends on some source of usable energy, and on Earth, the overwhelming majority of that energy traces back to sunlight, captured by photosynthesis in plants, algae and certain bacteria, and passed up through food chains from there. A world with no sunlight at all, which is exactly what a starless planet or moon is by definition, cannot support photosynthesis and cannot support anything that depends on it. This much is not in serious dispute. What is genuinely established, however, and this is the crucial fact that reframes the whole question, is that photosynthesis is not the only energy source life on Earth actually uses. In 1977, researchers exploring the deep ocean floor near the Galapagos Islands aboard a submersible discovered something unexpected at a hydrothermal vent, a fissure in the seafloor where mineral-rich, superheated water escapes from below Earth's crust. Dense, thriving communities of organisms including tube worms, clams and shrimp, living at depths where sunlight has never once reached, supported entirely by bacteria that derive energy not from light but from chemosynthesis, a process that extracts usable chemical energy directly from compounds like hydrogen sulfide dissolved in the vent fluid, converting that chemical energy into food in roughly the same functional role sunlight plays for a photosynthetic plant. This was not a hypothetical possibility proposed by theorists. It was, and remains, a directly observed, thoroughly studied ecosystem, one of several dozen known hydrothermal vent communities now documented around the world's ocean floors, existing entirely independent of sunlight, entirely independent of the sun's energy in any form. The relevance to a starless world's tidally warmed ocean should be immediately clear. A subsurface ocean on an ejected gas giant's moon, warmed by tidal flexing rather than sunlight, and potentially in contact with a rocky seafloor rich in minerals, the same basic geological setting that produces Earth's own hydrothermal vents, would in principle offer a broadly similar energy landscape. No sunlight anywhere, but a real, ongoing source of chemical energy at the boundary between liquid water and mineral-rich rock. Whether that energy landscape is actually sufficient to have given rise to life in the first place, as opposed to merely being able to sustain life that already exists there by some other means, is a considerably harder and much less settled question, one that touches directly on the broader, still unresolved scientific question of how life on Earth itself first began, a question researchers have not conclusively answered even for our own planet's well-documented history. It is important to be precise about what can and cannot be honestly claimed here. Astronomers and astrobiologists studying this question generally agree that the physical conditions plausibly present on a tidally warmed subsurface ocean moon, similar to what current evidence suggests exists on Europa and Enceladus within our own solar system, and potentially replicated on a starless, ejected version of a similar moon, are not obviously incompatible with the kind of chemistry life depends on. They do not claim, and current evidence does not support claiming, that any such environment definitely does, or even probably does, host life. The honest scientific position is a real but bounded one. Nothing currently known about the physics of a tidally heated, starless ocean moon rules out the possibility of life there, and Earth's own deep-sea hydrothermal vent ecosystems demonstrate that sunlight-independent life is not merely theoretically conceivable, but actually demonstrably real, at least in the one setting, Earth, where we have been able to look closely enough to check. This is very likely as far as the science can honestly take the question for the foreseeable future, given how difficult even confirming the existence of a specific starless moon would be, let alone sending any kind of probe to examine what, if anything, might be happening beneath its ice. What the question does accomplish, regardless of whether it is ever definitively answered, is to widen considerably what astronomers mean when they use the word habitable. For most of the history of the search for life beyond Earth, habitability was framed almost entirely around distance from a star, the the so-called habitable zone, where a planet's surface temperature allows liquid water without a star's heat being either too weak or too strong. The starless planets and moons this episode has been describing suggest that framing, while still useful for the specific case of surface liquid water on a star-bound world, may capture only a fraction of where the actual conditions for life could exist across the galaxy as a whole. Everything this episode has described so far, ejected planets, isolated collapsed ones, tidally warmed moons, has been discussed in the general case applying across the galaxy as a whole. It is worth asking, briefly, whether any of it applies closer to home, to our own solar system's own history and its own present-day outer reaches. On the history question, the evidence is reasonably strong that our solar system did, in fact, go through a version of the violent early instability described earlier in this episode, though almost certainly on a smaller and less dramatic scale than many other systems appear to have experienced. The already mentioned Grand Tack, the migration of Jupiter inward and then back outward during the solar system's first few million years, is understood as evidence of significant early gravitational upheaval among the giant planets, upheaval strong enough to have plausibly scattered a considerable amount of smaller debris, and possibly even a full-sized planet if one existed among the early giants in a configuration less stable than the eventual one that survived. A separate, later episode of instability, sometimes called the Nice model after the French city where the researchers who proposed it are based, describes a rearrangement of the outer giant planets, Jupiter, Saturn, Uranus and Neptune, that current models suggest happened several 100 million years after the solar system's initial formation, and that some versions of the model suggest could have involved the loss of one additional ice giant planet, ejected entirely out of the solar system during the rearrangement, though this specific detail remains one plausible variant among several competing versions of the model, rather than a settled conclusion. If our own solar system did eject a planet at some point in its history, current models offer no way to identify what became of it afterward. It would, by now, having had over 4 billion years to drift, be somewhere among the general starless planet population this episode has been describing throughout, indistinguishable in principle from any other rogue world of similar mass and age, its specific origin in our own solar system's youth, long since erased by the sheer scale of galactic distances and time. On the present-day question, there is a separate and actively debated possibility that deserves mention, though it must be stated with real care about what is, and is not, currently established. Since around 2014, several astronomers, most prominently a team led by Konstantin Batygin and Michael Brown, have pointed to an unusual clustering in the orbits of several small icy bodies far beyond Neptune. In the distant region, sometimes called the scattered disk, that current models suggest is difficult to explain through chance alignment, or through the known gravitational influence of the 8 confirmed planets alone. Their proposed explanation is a currently unseen, roughly Earth to Neptune mass planet, informally nicknamed Planet 9, orbiting the Sun at an enormous average distance, plausibly several hundred times Earth's distance from the Sun, far beyond even Neptune's orbit, on a long, slow path that current models suggest could take somewhere in the range of 10,000 to 20,000 years to complete a single full circuit. To make that distance graspable, Neptune, the outermost confirmed planet, orbits the Sun at an average distance of about 4.5 billion kilometers. The hypothesized Planet 9, on the low end of the proposed distance range, would orbit at something like 10 to 20 times that distance, and light itself, travelling at its constant speed, would take the better part of a full day just to cross the gap between the Sun and an object that far out, compared to the roughly 4 hours light takes to reach Neptune. It is essential to be clear that Planet 9, as of this recording, has not been directly observed. No telescope has photographed it, and the hypothesis rests entirely on the indirect gravitational evidence of the clustered orbits it is proposed to explain, evidence that remains consistent with the hypothesis, but does not on its own confirm it. Several alternative explanations, including selection effects in how the clustered objects were originally discovered, and even, more speculatively, the possibility of a captured, formerly starless object, rather than one that formed with the rest of the solar system, remain under active discussion among researchers. Whether Planet 9 exists, and if it does, whether it is a normal planet that formed with the rest of the solar system, or, intriguingly, an interloper captured from interstellar space at some point in the solar system's history, a possibility a small number of researchers have specifically raised remains genuinely unresolved, and is likely to stay that way until a survey telescope sensitive enough either directly detects it or definitively rules it out. This last possibility, a captured rogue world rather than an original solar system planet, connects the entire episode's argument directly back to our own solar neighbourhood in a way that feels almost too neat to be a coincidence. Though it remains, for now, only one hypothesis among several. If starless planets really are as common across the galaxy as the population estimates discussed earlier suggest, then it becomes at least plausible, rather than exotic, that our own solar system's gravity could have captured one at some point over its 4.6 billion year history, simply by chance, during one of the enormous number of close passes any solar system experiences, with other objects drifting through the galaxy over that much time. Every thread this episode has followed, the violent gravitational scattering that ejects a planet from its birth system, the quiet isolated collapse that builds one directly from a cloud with no star ever involved, the brief flickering microlensing signature that is often the only trace either kind of object ever leaves, the internal heat that keeps some of them from freezing completely, and the tidally warmed oceans that a fortunate few might carry beneath an icy shell, converges on a single genuinely significant conclusion about what a planet actually is, in the broadest sense the word can mean. For most of the history of planetary science, a planet was studied almost entirely in the context of its star, because a star was, practically speaking, the only way to find one. That practical limitation shaped the underlying assumption for a long time, that orbiting a star was not just how we happened to find planets, but something close to what a planet fundamentally was. The population estimates that have emerged from over a decade of microlensing surveys, however uncertain the specific numbers remain, point toward a different and considerably larger picture. Planets that never had a star, or that had one and lost it early in a violent and largely invisible process, may not be a strange minority case at all. They may, when every formation pathway and every size range is eventually accounted for, turn out to be the single most common outcome for a planet anywhere in the galaxy, simply because the galaxy has had 8 billion years and hundreds of billions of star systems in which to generate them, through a mechanism gravitational scattering among giant planets, that current evidence suggests operates in a meaningful fraction of all young systems. This reframing matters beyond simple statistics, because it changes what the search for life beyond Earth should honestly be looking for. The search has, understandably, focused overwhelmingly on the habitable zone around other stars, the region where a planet's surface could plausibly hold liquid water warmed by starlight. That focus remains entirely reasonable, since a starbound world with liquid water on its surface is by far the easiest kind of potentially habitable environment to detect and study from Earth. But if tidally warmed subsurface oceans, sealed beneath ice on a moon that no longer orbits any star at all, are even a modest fraction as common as the population estimates in this episode suggest they could be, then the habitable zone, as conventionally defined, may represent only one comparatively narrow slice of where the actual conditions for life exist across the universe, with a potentially much larger population of candidate environments sitting in the dark, tidally warmed interiors of starless wanderers that current search strategies are not yet equipped to find at all. The technology to meaningfully close that gap is, encouragingly, already being built. The Nancy Grace Roman Space Telescope, an infrared observatory developed by NASA and scheduled to begin its primary survey operations later this decade, is specifically designed to conduct a much larger, more sensitive microlensing survey than anything flown before, monitoring hundreds of millions of stars toward the galactic bulge continuously over an extended mission, with a sensitivity current mission plans suggest should be capable of detecting free-floating planets down to roughly Earth's mass, a full order of magnitude below the Jupiter-sized threshold, that has limited essentially every microlensing survey conducted so far. Separately, the European Space Agency's Euclid telescope, already in operation, and a range of upcoming ground-based infrared observatories with increasingly sophisticated adaptive optics, are expected to expand the small existing catalogue of directly imaged, young starless planets considerably over the coming years, extending the technique described earlier in this episode to fainter, and therefore either older or lower mass, objects than have been reachable so far. What these upcoming surveys are likely to establish within the coming decade is not a final, definitive count of the galaxy's starless planet population, The true number, given how difficult these objects are to detect even with dramatically improved instruments, will likely remain uncertain within some meaningful range for a long time yet. What they should establish, with considerably more confidence than currently exists, is the general shape of the answer. Roughly how the population scales with an object's mass, roughly what fraction formed through ejection versus isolated collapse, and roughly how many of the largest, most promising candidates, the tidally warmed gas giant moons discussed earlier, might exist within a distance close enough that some future, more capable instrument could eventually attempt to study one directly. Until then, what this episode leaves us with is a genuine shift in how to picture the galaxy at night. The stars visible to the naked eye, and even the hundreds of billions more that current telescopes can catalogue, are only ever the planet's visible companions, the convenient landmarks that happen to make a nearby planet easy to find. Scattered between and around every one of those points of light, current evidence increasingly suggests drifts a population of worlds that belong to no star at all, some still carrying the fading warmth of their own violent departure, some that were never anything but alone from the moment they formed, and a small, genuinely uncertain number that may, right now in total darkness, be keeping something alive. Every planet we can name with confidence orbits a star. Earth does, Jupiter does. Even the coldest, most distant dwarf planets in the outer solar system trace some kind of loop around the Sun, however slow and however wide. But that turns out to be a description of the planets we happen to be able to see easily, not a description of what planets in general actually are. Somewhere between 1 and several times the population of the Milky Way's 400 billion stars, current estimates suggest there may be planet-sized bodies with no star at all, worlds thrown clear of their birth systems by a near miss with a larger sibling, and worlds that never had a system to be thrown from, having condensed straight out of the same clouds of gas and dust that make stars, only falling short of the mass needed to ignite. Neither kind announces itself. They carry no light of their own, beyond a faint residual glow of formation heat, fading over hundreds of millions of years, and they can only be caught in the brief seconds when their gravity bends the light of something behind them, or in the rare case where a young one is still warm enough to be photographed directly against the dark. What we have found so far is almost certainly a small fraction of what is actually out there. If the current estimates hold up, then the galaxy's population of planets was never really organised around its stars at all. Most planets, on this accounting, may spend most of their existence belonging to no one, keeping their own private darkness, their own private warmth, and possibly, in a small number of cases we cannot yet rule out, their own private chemistry, quietly working away with no sun ever rising to see it.